Okay. So we had got to the point where we had found the laws of black hole mechanics that looked suspiciously like the laws of thermodynamics. So the real question is, are they actually the same thing? So let me remind you of a piece of quantum field theory. Suppose that you're interested in calculating Green's functions in the canonical ensemble. Then what you would be interested in doing would be calculating something like g of positions in space, and if we're in the canonical ensemble, there must be some kind of symmetry involving time translation, simply because the thing is in equilibrium, nothing is happening, and so the Green's function will only depend on the difference between two times, t minus t prime. And this kind of thing will be equal to the expectation value of two fields in the canonical ensemble, characterized by an inverse temperature beta, so that's equal to 1 over t. And the way in which you calculate these things is to say that this is really the same thing as the trace over all states of e to the minus beta times the Hamiltonian, phi of x t, phi of x prime t prime. The easiest way to understand what we want to do is to calculate some properties of this function, and I'm going to use the Heisenberg picture for the fields. So in the Heisenberg picture of time evolution of any operator, including the field operators here, is simply given by conjugation with the Hamiltonian. So that if you wanted to find a time translated field, you just simply conjugate with the Hamiltonian and you'd have an e to the minus ih tau, phi of xt, e to the plus ih tau. So armed with that information, you can say, well, if things are appropriately analytic, there's absolutely no reason why tau should be real. And so you can analytically continue tau to a complex variable. And discover that if you put tau equal to I beta, make sure I got my sign right, then this is equal to e to the h beta, phi of xt, e to the minus h beta. Given this, we can calculate what happens if we translate t minus t prime by an amount I beta. So let's do that. G of x g of x prime t minus t prime plus I beta is going to be equal to the trace of e to the minus beta h, phi of x t plus I beta, phi of x t prime. Then what you can do is to take this relationship here and plug it into this object, and you'll get trace of e to the minus beta h, e to the beta h, phi of x t, phi of x prime, sorry, of x prime t prime. We missed out an e to the minus beta h. These two objects cancel, and so this thing is just a trace of phi e to the minus beta h phi. So since these objects are invariant under cyclic permutation under the trace. This is the same as trace of e to the minus beta h phi of x prime t prime phi of xt. And so this thing, since these things commute at space-like separations, you can always send these the other way around. And so this is equal to g of x, x prime, t minus t prime. Same is true for any other correlation functions you care to construct. It really doesn't make any difference. What you have discovered is that the Green's function, or any correlation function constructed in a similar way, is periodic under translation in imaginary time with period beta. This is the so-called Kubo-Martin-Schwinger condition, or KMS. And their principal contribution was to make the argument here work in the other direction, namely that if the Green's functions were periodic in imaginary time in this way, they must have been computed in the canonical ensemble. Proof of that is rather difficult, but essentially it's sort of how you go about reversing this process. So armed with that, let's go back and look at the Schwarzschild metric. Suppose that we were trying to do quantum field theory in the Schwarzschild background. Well, you'd start with the metric for the Schwarzschild space-time. And you'd say, well, I want to compute the Green's functions in this background. So what you might be inclined to do would be to construct the mode functions and do some kind of sum. However, you will discover that the mode functions can't be written down in a nice form in the Schwarzschild metric. The radial part of the wave equation is horrible. It's a version of the Hoyne equation, which doesn't have nice integral representations. All you can do is to deal with series solutions. So this is an impractical thing to do. What you can do instead is to simply say, well, what would happen if I tried to do that calculation? Well, the one thing that you do know from quantum field theory calculations just in flat space is that you can start off in Euclidean space after doing a Wick rotation, use analyticity to find the Green's functions that you're interested in. So the idea here would be to do the same. Wick rotate, compute the Green's functions, and then analytically continue. So let's just do it. You would send t to I tau, and ask yourself, what happens now? The metric then becomes ds squared is plus 1 minus 2m over r d tau squared, plus the same thing to the minus 1, dr squared, plus r squared d omega 2 squared. So you're now faced with the same problem that you had before in the ordinary black hole space-times. R equals 2m is a singular point. Well, it's singular, it's not really a point. But unlike what happens in a Lorentzian signatured space-time, r less than 2m really can't be part of this space. If you consider what happens for r greater than 2m, r greater than 2m, this thing has got signature plus 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 plus, and certainly has something to do with what happens at infinity. But if you ask what happens for r less than 2m, this object becomes negative, and whatever the space is has got signature minus minus plus plus. So that tells you that this thing really can't be part of the same manifold as this. So this you just simply forget about. It must be some disjoint object. So you forget about it. But you're still left with asking what happens for r greater than 2m. Let's, strictly speaking, we should include the point 2m in this. There is a singularity here, but if you calculate the Riemann tensor, you'll discover that the square of the Riemann tensor is bounded. This thing looks like m squared over r to the 6th still. So at r is equal to 2m, this is proportional to 1 over m to the 4th. So nothing peculiar happens. So we need to investigate the nature of this singularity. The easy way to do this is to make a little expansion about r equals 2m and see what happens. So I'm going to make a coordinate transformation. R is equal to 2m plus rho squared over 8m. And we're going to treat rho as a small thing. And ask ourselves what the geometry is going to be near rho equals 0, because the coordinate singularity at r equals 2m has been mapped into rho equals 0. It's kind of easy. dr is equal to rho d rho over 4m. 1 minus 2m over r is equal to rho squared over 8m divided by r, which is roughly speaking 2m plus other stuff, so we can forget about that. So this is roughly speaking rho squared over 16m squared. And let's substitute that into our metric. If we do that, we'll get ds squared is equal to, from here we get rho squared over 16m squared d tau squared, because we just substitute in 1 minus 2m over r. Here we'll get the same thing the other way up, 16m squared over rho squared, dr all squared, but dr is rho d rho, so we get rho squared d rho squared over 16m squared, plus from here 4m squared d omega 2 squared. And you'll see that all these things cancel out nicely, and you're left with d of rho squared sitting outside the front, d of tau over 4m all squared, plus d rho squared, plus 4m squared d omega 2 squared. So this is something that you should recognize. This is basically a product space near r equals 2m, in which you have here just a two-sphere of radius 2m, and here, well, this is just the metric on flat space. But written in polar coordinates. There is, of course, an issue with this thing. It's only the metric on flat space if you identify this thing with an angular coordinate. So normally you'd write this as d theta squared, and you'd identify theta with period 2 pi. So you'd have to identify tau over 4m is identified with period 2 pi. But you might ask, what happens if you didn't do that? Well, just look at the rho tau plane. So here is the rho tau plane. So rho is a distance from the origin. So you could pick the origin to be here. Then rho is the distance out there. Tau then controls the angle that you go round here. So the angular variable here would be tau over 4m. Suppose you didn't identify it with period 2 pi, but you identified it with period 2 pi minus delta. What would happen in this picture? Well, the answer is, of course, that you take this point, you construct a circle round here, and this angle would be delta. Then you identify these two lines, but if you do that, then what you have done is that this thing isn't something that you can draw in flat space. If you try to extract it, you'll end up with basically a cone, and it's called a conical singularity. You can demonstrate this with a piece of paper fairly easily. If you want to construct this thing, then if you embed it in R3, then it will look something like this. And then this point is the same as that point. So this piece of paper would be flat, except at this point. This is known as the conical singularity. It gives you a delta function in the curvature. So that would be an honest singularity, and in the spirit of general relativity we don't like singularities, so we just simply say that's not what's supposed to happen. It wouldn't, for example, solve the vacuum Einstein equations. Remember that those are just going to be RAB equals 0. Instead you'd have RAB as some kind of delta function. So you identify tau over 4m with period 8 pi. That means that you identify tau with period 8 pi m. That means that any Green's function you care to calculate on this space will have periodicity in tau period 8 pi m. That tells you that from the KMS condition then implies that what you've actually done is you performed a calculation in the canonical ensemble with a temperature of 1 over 8 pi m. So, yes. We're not, we're just making life easy for ourselves. So, what have we discovered here? We've discovered that if we do a calculation in the canonical ensemble, we've got a gas of whatever it is, whatever particles we're considering, that is in thermodynamic equilibrium with the black hole. So from the zeroth law of thermodynamics, you conclude that the black hole has a temperature of 1 over 8 pi m, because the two things are in equilibrium. Let me remind you of the first law of black hole mechanics now. dm was equal to kappa dA over 8 pi plus phi dq plus omega dj. We did a calculation for the Schwarzschild metric where these two are both 0 and discovered the temperature was equal to 1 over 8 pi m. But we also know that kappa is equal to 1 over 4m. So it looks as if the temperature is equal to kappa over 2 pi. If you want to do a more complete calculation, you have to take the hint we were just given and do the calculation in the grand canonical ensemble so that you can take account of these potentials phi and omega. I'm not going to do that because the way in which it works is almost exactly the same way as it does for the canonical ensemble. And whatever you do, you will always discover that the temperature is equal to kappa over 2 pi. That's a universal result. So if you thought that this was really TdS, which is what you should now think, that tells you that S is equal to A over 4. This temperature was originally discovered by Hawking in a completely different way, which is rather more complicated than this. It's sufficiently complicated that I don't actually want to reproduce it here, but basically it involves finding approximate solutions to the wave equation in the Schwarzschild space-time and exploring their properties. This is somehow a lot easier. The result is the same. You discover that T is kappa over 2 pi and the entropy is equal to A over 4. Famously, Boltzmann has written on his gravestone S is equal to K log W, the number of ways in which you can find something that has entropy S. Hawking wants A over 4 to be written on his gravestone. The question then is, what does this entropy really mean? Well, there's a nice way of calculating it, again from the canonical ensemble, that sheds some light on this. So again, we will just simply look at the Euclidean version of field theory and ask ourselves about the path integral in gravitation. So you would say it's something like the integration over the space of all metrics, exponential of I times the action. Something like that. But you can reinterpret this in the following way. You can reinterpret this in the canonical ensemble by saying this is the integration over the space of all Euclidean metrics that are periodic in imaginary time. Well, periodic in of e to the minus action. In which case, this z is just equal to the canonical partition function, and is e to the minus free energy divided by the temperature. What is the action? We all know the bulk form of the action. The action is just going to be equal to minus 1 over 16 pi integral scalar curvature square root of g d4x. The Einstein-Hilbert action. But actually that probably isn't really what you want to do. You usually think of some bit of space-time here, and the kind of calculation that you want to do is to extremize the action as you vary the metric, but you need to fix some boundary conditions to do that. Otherwise you don't have a self-adjoint problem. So what you need to do to have a proper action would be to say, well, I'm going to have a boundary here, and the metric will be fixed on this boundary. And let's just say that the metric on the boundary will be h. That means that the variations, when you look at the variation of r, have got to cancel for these boundary conditions. And this means that you will have to introduce a term 1 over 8 pi g times the trace of the second fundamental form on the boundary. So this is over m. This is over the boundary of m. This term was discovered by Jim York back in 1972, and of course as a consequence was always known as a Gibbons-Hawking boundary term, to which you can add, of course, any functional of the boundary metric you like, and it doesn't make any difference to the variational problem. Armed with all of this, let's imagine we calculate this thing for the Schwarzschild black hole. We already know what this metric is, so let's go back and look at this metric. The Euclidean Schwarzschild metric is ds squared is equal to 1 minus 2m over r dt squared, d tau squared, plus the same thing to the minus 1 dr squared plus r squared d omega squared. It obeys the vacuum Einstein equation, so RAB is equal to 0. And so if you start trying to evaluate this thing, you would say, oh, well, it's e to the minus the action of the Schwarzschild metric fine, into 1 plus quantum corrections. So what would you do? You evaluate this, and this will be the most interesting contribution, and then there'll be some quantum corrections which you could in principle evaluate, but might find it difficult because the theory is not nice in the ultraviolet. So let's evaluate this action. The metric is Ricci flat. That means that the Ricci scalar is equal to 0, and so this doesn't give you anything. You are then left with this term here, the integral of the second fundamental form on the boundary, and that will give you something. Let's quickly calculate what it actually is. So the way to do this is to fix the metric on the boundary. So what do we know about this metric? This metric here is going to be G restricted to R equals some very large radius r out near infinity. Remember, it is periodic in imaginary time. So tau is identified with period 1 over 8 pi m. How do we calculate the second fundamental form? Well, k is just equal to the divergence of the unit normal to the boundary. So you need to construct the new unit normal to the boundary here, NA. So it just points in the radial direction. So if you do that, you will discover that NA with its index downstairs is equal to 0, 1 minus 2m over r to the minus a half, 0, 0. And NA with its index upstairs is therefore 0, 1 minus 2m over r to the plus 1 half, 0, 0. And if you calculate its divergence, you will get the following object. Evaluated on the surface r equals big R, you will get 2 over r minus m over r squared. Now let's look at, that's k. Now let's look at h. H is the determinant of this piece metric. So the determinant square root of h is going to be equal to 1 minus 2m over r times r to the fourth sine squared theta to the 1 half. And so you can immediately see that this integral will diverge. Evaluated at big R, this will just give me an R there. This thing will be equal to approximately 4 pi times the periodicity, which we'll call beta, and then there will be a term which looks like 2r, and then there will be a minus 3m, plus stuff which dies off as r goes to infinity. So this integral is divergent as r goes to infinity. And so you'd be inclined to give up. However, we should be a bit braver than that. After all, we're doing physics, not mathematics. And sometimes you need to take emergency measures. We've already taken it. Here, there is a C of h. This is some unknown functional of the metric on the boundary. What do we imagine is going to be true? We would almost certainly imagine that the action of flat space is 0, because nothing happens in flat space, at least classically. But if we thought that, then we just look at this calculation and discover that it would diverge as well. So the trick is to subtract off here something which will cancel the effect of what happens in flat space. So choose C of h to be equal to plus 1 over 8 pi integral over the boundary of the trace of the second fundamental form in flat space square root of h d3x, where the metric on the boundary is the same as the metric for the Schwarzschild solution. So how do you find a metric which is the same? Well, it's very easy. You just stare at this formula and say, a metric that is going to be the same and is flat will be we're not interested in what happens in the r direction. That's perpendicular to this orange circle. So the boundary metric for flat space would be 1 minus 2m over r fixed d tau squared plus r squared d omega 2 squared. This thing is fixed, so it's just a rescaling of the time coordinate. This thing is the same as that thing, and the metric on this is flat. Notice this r is fixed, so there is no coordinate singularity, and again tau will be identified with period beta. If you do that calculation, you will discover that the integral of k square root of h d3x over dm, but now in flat space, is going to be equal to 4 pi beta into 2r minus 2m plus higher order junk, which we don't care about. So that tells you what the action is going to be. You just simply subtract the two, and of course this infinite piece, as r goes to infinity, will cancel, and you will get the following result for the action. You will discover that the action is equal to a half m beta once the dust settles and you put in all the factors of 8 pi. This is supposed to be equal to e to the minus free energy over the temperature. Sorry. So what you discover is that let's write it a different way, m over 2t. So that tells you the free energy is equal to m over 2. Now let's think back to some elementary thermodynamics. The free energy is equal to the total energy, U, minus Ts. The total energy for this system is just the mass of the black hole. There isn't anything else there. So this is equal to m over 2. That tells you that S is equal to well, the simple thing to do is just substitute in t, which we know to be 1 over 8 pi m. This is equal to 4 pi m squared, which is the same as a quarter of the area of the event horizon. So what you discover is a calculation of the entropy of the black hole. Again, you can generalize this to the grand canonical ensemble and produce a general version of the same calculation that will produce S equals a quarter A under all circumstances. And the result is that S is always equal to 1/4 A. There is one disadvantage of using natural units throughout these calculations. Recall that we put h bar equal to 1, almost always. What would happen if we put the h bars back in? Firstly, if you look at the temperature, you will discover it is h bar kappa over 2 pi. If you look at the entropy, it is A over 4 h bar. In a classical world, h bar goes to 0. So what you would say classically is that T would go to 0. That corresponds to the way in which you think about black holes as universal absorbers that emit nothing. T is equal to 0. Similarly, S here would go to infinity, reflecting the fact that the uniqueness theorems tell you that, at least classically, a black hole is completely independent of its method of formation, apart from a knowledge of M and J and Q. So these results are precisely what you would expect from completely classical reasoning. Nevertheless, if h bar is not equal to 0, you are faced with the problem of understanding what this A over 4 h bar really is. Boltzmann told you that this is supposed to be the logarithm of the number of ways in which you could have produced this state, and we simply don't know how to calculate W. There is a calculation of Strominger and Waffer that tells you a little bit about this in the case that T goes to 0, where you can regard 0 temperature black holes as being made up of microstates made of brains. That calculation works, but the calculation really only works in the limit that big G goes to 0, and so that's a little unfair. If we put big G back in here, we'll discover a G in the denominator, and so we should feel a little bit suspicious about that. Nevertheless, it's an interesting and fairly convincing explanation, but it doesn't work when T is not equal to 0. The fact that black holes have a temperature that isn't equal to 0 leads to some kind of disasters. Essentially, it leads to what is usually called black hole evaporation, and following on from that, the information paradox. So let's see if we can understand what that really is. Suppose that a black hole forms. Let's go back to this diagram, which is actually sometimes called the red herring diagram. So a black hole forms, there is a singularity somewhere inside it, there is an event horizon, which looks something like this. But instead of having zero temperature and lasting forever, let's suppose that we have vacuum out here. What will happen? Well, the black hole is hot. It has some kind of temperature which is proportional to 1 over m, at least in the case that it's not rotating or charged. And so it will emit black body radiation. At a temperature T, which is equal to 1 over 8 pi m. That means that the thing will lose energy. As it loses energy, its mass will decrease. So you can calculate dm dt. It's what you'd get from black body radiation. It's a loss of energy. For each species of particle, you will have a sigma t to the fourth times the surface area of the black hole. That's not quite right, because the only species that is going to be radiated in any significant quantity will be those that have a mass of less than the temperature. So this is species of mass less than T. Approximately that at any rate. T looks like 1 over m. The area looks like m squared, and so this whole expression looks like minus some constant over m squared. So what happens is that the thing loses mass, and as its mass decreases, the rate of loss of mass increases. That's because its temperature increases as the mass goes down. So there will be an explosive evaporation process, and then eventually you're left with nothing but radiation. This reflects the universal instability of self-gravitating systems. Remember that the mass is equal to 1 over 8 pi times the temperature. So if I calculate the specific heat, that's dm dt, I will discover that it is negative, and that's a sign of instability. The instability is due to production of radiation. The red black body radiation that is produced is sometimes called Hawking radiation. And its detection would be a monumental achievement. There are condensed matter systems which should exhibit similar phenomena, and the analogue of Hawking radiation is claimed to have been detected in some condensed matter systems, but I don't know whether or not, well, such claims are not universally believed, and I don't know whether to believe them or not. We ought to put some kind of timescales to this, because as things stand, this is just some abstract business. The easiest way to do this, of course, once you've got one scale fixed, you can figure out everything else, because you know the lifetime is of order m cubed. The temperature is order 1 over m, and so everything else you can figure out by scaling. A mass of 10 to the 15 grams, roughly the size of a small mountain, corresponds to a temperature of 10 to the 12 degrees absolute, which, if you think about it, is the same thing as the mass of the pion, roughly. Or, alternatively, the strong interaction scale. And corresponds to a lifetime of roughly 10 to the 10 years. Or 1 Hubble time, if you prefer it. This is easy to remember, and everything else you can get by scaling. The reason that it's going to be very hard to see Hawking radiation in astrophysical systems is because if you took the mass of the Sun, which is 10 to the 33 grams, and asked what happens if you look for black holes of roughly solar mass, their temperature would correspond to 10 to the minus 7 Kelvin, which is vastly lower than the temperature of the CMB, so this is kind of hopeless. There are some cleverer things that you might do, but they're not things that are going to be easy to do. So I think we just leave it there in terms of astrophysics. Let's draw a Penrose diagram of this evaporating black hole process. You will see that there's one small part of that which gives rise to a difficulty, which is usually ignored. So you can form a black hole in the usual way, just by collapsing matter. But now the black hole will evaporate. That doesn't look very good. Something like that. So the radiation really comes from close to the horizon, not actually from inside the black hole. It would be unfair to say the radiation came from inside the black hole. So as you move up here, what you will see is radiation, and then it will suddenly stop. There is a small difficulty here because this point is singular. We actually almost managed to prove that yesterday because we looked at the area theorem. The area theorem told us that dA by d lambda was positive or 0, provided the energy momentum tensor of matter was positive. Well, of course, here what's happening is that the area looks like m squared, and we've discovered that m squared is going to 0. And we had some circumstantial evidence that if A was actually 0, something singular would be going on, and that's precisely what is happening here. So this is an example of a naked singularity and is potentially problematic. But we're all so accustomed to imagining that energy conservation is true that you don't worry about it, and you simply assume that energy conservation works in this space-time, despite the fact there is a naked singularity. Nevertheless, the second law of black hole mechanics is being violated. Why? Well, the answer is kind of obvious. There is radiation here going off to infinity that is carrying away the mass of the black hole. How can that happen? Well, it can only happen because the flux of energy across the horizon, that way, must be negative. So the energy density of, when you think about it, you see the energy of this whole thing must be 0. So the energy that is going off to infinity must be cancelled by negative energy flowing in through the horizon. Detailed calculations of the energy momentum tensor in quantum field theory support that conclusion. So this comes about because in quantum field theory you can't guarantee that the energy density is positive. And here is an example. If you think that is alarming, you can also think about the Casimir effect. And in the Casimir effect, you have negative energy densities, and they don't bother you, and you can measure it. Yes? In this picture, you have somehow removed any idea of causality from what's going on. The problem is that this line here, though it looks like something which is happening in time, is in fact a space-like surface. So that's why when you usually draw things in terms of the Penrose diagram, and it's also why this is usually called the red herring diagram. It's called the red herring diagram because it's misleading. You really want to think in terms of this picture, but you're really asking, where does the Hawking radiation come from? Does it come from here? Does it come from here? Or what? The answer is that you don't really know. I think it really comes from close to the horizon, because the radiation doesn't depend on the details of the collapsing body. To see that, you really have to do this calculation the way Hawking originally did it, and I don't think we have got time for that. You can invite me back to explain that calculation if you like. The problem, so-called information paradox, is basically the following problem. Suppose that you're interested in calculating an S matrix for black hole evaporation. What would happen to you? Well, the S matrix is basically a map between in states and out states. So an in state would be defined along a line that looks something like that. An out state will be defined along a surface that looks something like this. These things would include these points at I minus and I plus, as well as null infinity and in both the past and the future. It does not include the point I0, which I should really erase from here. These lines do not join up. Let's make it a little bit. That's because you can't make observations at I0. You do not go to space-like infinity to look at anything. So you're really interested in maps between here and here. What you have learnt from the classical picture of black hole evaporation is that all information about the incoming state here has been erased by the horizon. The horizon only being characterized by M and J and Q. So that means that you could start here with a pure state. You wait for a long time, and what you see is just the Hawking radiation up here, which you believe to be thermal. If you calculate the von Neumann entropy of the incoming, you'll discover that this is equal to 0. If you calculate the von Neumann entropy of the outgoing Hawking radiation, which is all you have left, it would appear, it's minus the trace of rho log rho, where rho is a density matrix which gives rise to describes the radiation, and whatever this is not equal to 0. But in quantum mechanics, you can't change the von Neumann entropy because you have unitary time evolution. So this picture is in conflict with the elementary laws of quantum mechanics. That's the black hole information paradox. Where such invalidations of quantum mechanics to actually happen, I think we would have noticed. The reason being that in any process involving gravitation, you would expect to find virtual black holes, their contribution to amplitude to be very small, but they would give rise to violations of unitarity. If unitarity is violated, symmetries of a Lagrangian would give rise to conserved charges, and so Noether's theorem wouldn't work. And the one thing that we do know is that it does work. In particular, energy would not be conserved, momentum would not be conserved, electric charge would not be conserved. everything that we know and love wouldn't work. So this can't be right. What are the things that have been suggested? It seems to me that there are really three ways that have been talked about of getting out of this problem. Let's deal with them all turn by turn. So one possibility in actual fact, I don't really think any of them make sense, but well, two of them certainly don't make sense. So, possibility one that has been discussed, remnants. Instead of evaporating completely, the black hole produces a small remnant. The Hawking radiation turns off at some particular temperature, and so the correct version of the Penrose diagram looks something like this. This doesn't help, because it's still the case that in the region that you observe, there will be a violation of unitarity. There is here a remnant black hole, but all of the information has got to be accessible to the outside if you're not to see a violation of unitarity. That's not what you see. Furthermore, if this picture is correct, anything that falls into the black hole will eventually fall off the space-time, because that's the boundary of the space-time. You will reach the singularity in finite proper time. And so, somehow, this can't really be right. It doesn't really solve the problem. Any black hole that is left would have to be able to contain an arbitrarily large amount of information in an infinitesimally small volume, and that also seems implausible. So I don't believe this. A modification of this is the baby universe scenario. Here you remove the existential problem of the singularity and replace it by some extra bit of space-time that you can't observe, sitting up here perhaps. Some cosmological model. But that doesn't work either, because you've still taken information away from our region of space-time. So that doesn't work. The only thing that could possibly work, as far as I can see, is if somehow the information never actually gets annihilated or absorbed inside the horizon. So somehow this picture is in need of some kind of modification where somehow you are able to see that information is preserved. In order for information to be preserved, you'd have to identify a collection of charges that contain the information. We don't know a complete way of doing that. But we do know that you can find extra charges associated with black hole space-times that go beyond what one expects in classical general relativity, or at least classical general relativity as usually presented. Let's illustrate this in the case of quantum electrodynamics. So the first step is to, yes? Yes? Mm-hmm. Sure. What you say is absolutely correct. So I go, well, not the end of the story, because you've still got to explain what happens to things that fall through here. You've got to explain where the information is. So that's what I'm going to show you a way of doing, but I don't know whether it's enough. Well, what you can do, and what people do is, well, let me remind you of something. So, the Einstein equations, you usually think of this thing as being classical. Now, what people have done, and this is because they have no quantum theory of gravity, they tend to say what you should do is to couple the Einstein tensor to the expectation value of the energy momentum tensor. This makes no sense. In fact, it's completely wrong, and you know it's wrong, because you just have to do one thought experiment, usually called the Page-Geiger experiment. It's a bit like Schrödinger's cat. You have an insulated room containing a huge lead weight and a graduate student. And the lead weight can be here or here. And there is an experimenter sitting outside with a Cavendish apparatus asking the question, where is this huge lead ball? And of course, we all know the answer to this question. Let's compute it in two different ways. Let's use this formula. This formula will tell you that the Cavendish apparatus will tell you it's in the middle, because if the probability of being here and here is equal to 1/2, then it will point to the expectation value, and so it will point to the middle. And we all know that's wrong. Doesn't happen. Which means that the Einstein equation is at best an operator equation. So a semi-classical quantization scheme is never going to tell you the answer. But if we take this thing as an operator equation, you've still got to find the operators which are appropriate to describing a map between here and here, which contain more information than we have described. And so that's what I want to briefly discuss. How you can have extra information, extra charges, if you like, associated with these surfaces. At the moment, we only have big Q and J and M, but in actual fact, we can have a whole lot more than that. So it's an identification of what these charges are that's important. So this is some recent work of Stephen Hawking, Andy Strominger, and myself. You can find one paper in Physical Review Letters from sometime in the summer, and a second paper was put on the web yesterday. So let's see what these charges are. Let's do the calculation in electrodynamics because it's much easier than doing the calculation in gravity. It doesn't make a whole lot of difference. Well, apart from some technical issues which I'm not going to get into. So the way this works is to consider scattering, and we're going to use some results of Christodoulou and Kleinemann. What they did was to take the vacuum Maxwell equations. You can do this with linearized gravity if you like. And what they did was to calculate the electric field here or, for that matter, the magnetic field. It doesn't make any difference. Asymptotically, so in other words, this is the contribution to the electric field that looks like 1 over r². And they calculate this as a function of position on the celestial sphere. If you think about what happens at the future endpoint of scry minus, then, which is where this red blob is, that's a two-sphere, and that two-sphere will have points on it. If you decide where the North Pole is, then you can simply say, well, this is some particular point on the sphere. Or gravitational. But you can also do the calculation at the past endpoint of scry plus, this other red point here. And what you discover is that it's the same function, almost. Except that if you calculated the value on the celestial sphere at the point P, then this function will take the same at the point P bar, where P bar is the point antipodal on the celestial sphere. In terms of polar angles, if P has got values theta and phi, then P bar has got values pi minus theta, phi plus pi. That reflects something interesting. It means that as you go between here and here, fields are discontinuous. But they're discontinuous in this predictable fashion. That reflects the fact that in the compactification of Minkowski space and things that look like it, I0 is a singular point. Scry minus means scry minus, plus means the future endpoint of it. This means the past endpoint of scry plus, but in a predictable way. And this reflects the fact that I0 is singular. So let's look at electrodynamics. The same is true in gravitation, but I don't think we're going to have time to do anything about gravitation, or not anything deep. So let's look at what happens at this point. At this point, we know what F is, electric or the magnetic field, the 1 over r squared term. We saw already that with a charge, Q is 1 over 4 pi times the integral of dsAb, FAB. We can generalize that. Perhaps a slightly nicer way of writing this expression would be to write it using forms. in which case we would say that this was equal to 1 over 4 pi into the integral of star f at on scry. F is the electromagnetic field strength 2 form. So that's just a rewrite of this expression using language of forms, which makes life a bit easier. We won't get bogged down with whole collections of indices. Have you come across differential forms or not? Yes. All right, good. Then we will use them. So what Christodoulou and Kleinemann tell you to do is to generalize this expression. They say there is a charge, q epsilon minus, defined at the future, I beg your pardon, it should be up here. It's the integral over the future endpoint of scry plus, sorry, the future endpoint of scry minus, epsilon times f. Epsilon is any spherical harmonic you care to think of. You can also find a charge defined at this point. This is an integral over the past endpoint of scry plus of epsilon star f bar. F bar is the antipodally mapped f. So what Christodoulou and Kleinemann proved, although this is not what they said, was that this is equal to that. The two things are equal. That tells you that there are an infinite number of charges which are conserved between here and here. One for each spherical harmonic. Now, in a black hole space-time, we can extend slightly our notion of an out state by extending this surface to be this, so it includes all of the future. It's still the case that Q plus is equal to Q minus. But now let's use Gauss's theorem to figure out how Q plus or Q minus can actually arise. Let's look on scry minus for the moment. You can define on scry minus the charge at any instant of advanced time. Advanced time is a coordinate which moves up here like that, minus infinity there, plus infinity there. And this thing is equal to q epsilon minus at v equals plus infinity, so it's the thing that you have here. And then by applying Gauss's theorem, this is equal to d epsilon star f plus integral of epsilon d star f. And these are integrals up scry in some interval between wherever this is and wherever and infinity there. So this is over the range between v and plus infinity. From Maxwell's equations, d star f is equal to star j. So this formula tells you how to evolve a charge as you move up here. So in other words, it tells you how to measure the charges. It's the same as doing Gaussian integrals as we did to describe the mass or the ordinary electric charge in the black hole spacetimes we've already looked at. Similarly, up here, this charge is equal to that charge. And so you can construct an evolution over this surface. This really corresponds to the origin of space, so you never get any contribution from here. And this point here is a point, so you don't get any contribution. Q here will be equal to 0. Because there's simply nothing there. So that means there's a full accounting for these charges throughout the space-time. In particular, you can always figure out what's happening here. There is evidence that at this point, Q is equal to 0 also. So that tells you that all of the charge that starts off here is going to end up here. Q is 0 there, because this too is a point, so that there can be no contribution from it, although it requires you to not worry about the naked singularity here. But we already had evidence we don't worry about that anyway. So here are an infinite collection of conserved charges in electrodynamics. We can interpret these two terms. This term here is simply due to currents flowing through the red surface. This term here is a little bit different. This you can attribute to soft photons. Soft means that zero energy. Photons on scry. So these charges give you an infinite set of conservation laws which the black hole will preserve. One could say a whole lot more about the nature of these soft charges, but I think I don't want to do that right now. You mean here? At I0. You mean, could we extend this up to there and that up to there? Well, it just simply stops you having continuous fields as you go between here and here. Yeah, so the fields here are antipodal to the fields here. For a complete proof of this, you have to go and look at Christodoulou and Kleinemann, but there is a simple example. So let me tell you about the simple example. Let's think about Minkowski space. And think about a point charge. If the point charge is not moving, then you would say the electric field is equal to Q over R squared. But we all know that if you have a radiating system or a charge that's moving, you should be using the Reissner-Nordstrom potentials to find out what the charge actually is and compute the retarded version's electromagnetic field. If the charge is not moving, then of course it's this always. But if the charge is moving, something a little bit different happens. First of all, the trajectory of the particle looks a little bit like that in the Penrose diagram. This is a charge moving at constant velocity v. Let's ask ourselves what ftr is going to be out near infinity. No, I don't want to do that. I want to work out what fur is near infinity. In other words, what is the value of the electric field up here? It doesn't matter where you are on Scri+, it's always going to be the same because the thing is moving with constant velocity. So you go and look in your copy of Jackson, and you will discover that this is equal to Q, 1 minus v squared over r minus v dot x, all squared. X being the spatial coordinate, v being the 3 velocity. So that's what you get from the Reissner-Nordstrom potentials. Anywhere on Scri+. But now suppose I want to compute this on Scri minus. UR theta phi coordinates are hopeless on Scri minus because U is infinite. This is the surface U equals minus infinity. So you don't want to consider that. You want to consider what FVR is instead. V being the advanced time coordinate, which is a good coordinate on Scri minus. So you go and look in Jackson again, change a few signs in the appropriate way, and you will discover that this is equal to this. For the same velocity. What is the relationship between these two things? Well, the answer is it's the same as sending x to minus x. And that's the same as the antipodal map. So that's an example of how it works. The results of Christodoulou and Kleinemann are more general than that, but unfortunately, if you've ever had any experience of reading Christodoulou's work, you will know that this is not so easy to follow. Laura Bieri, who's in the mathematics department at the University of Michigan, is working on a simplified proof, which I hoped would have appeared by now, but doesn't seem to have done. So I don't quite know what has gone wrong. Probably it's not as easy as she thought, but nevertheless, with a bit of luck, there will be some improvements in this soon. The Christodoulou-Kleinemann result is restricted to a particular domain that is an approximation to Minkowski space. I can't give you a precise description of what that domain is, but it's a finite domain, it's not an infinitesimal one. So, we have a whole collection of conserved electromagnetic charges. Can the same thing happen for gravity? And the answer is yes. There are a whole collection of charges for gravitation as well, and they come from the BMS group. Let me first of all describe them at Scri. There's a similar map between Scri plus and Scri minus, so I'll only tell you what they are on Scri plus. On Scri plus, the thing to do is to compute what the form of the metric is. So I'm going to use what are usually called Bondi coordinates. These are coordinates u, r, theta, and phi, arranged such that grr is equal to gra is equal to 0, and gab is equal tends to r squared gamma ab, where these symbols will become, meaning of these symbols will become apparent shortly. So the metric is minus 1 minus 2m over r du squared minus 2 du dr plus a quarter of r squared, r squared gamma ab plus rcab plus 1/4 of gamma ab cde plus higher order junk dza dzb plus dA CAB DZB du, and then plus some higher order stuff. So this line element represents the line element of a space-time that is evolving. It sort of looks a bit like the Schwarzschild metric, here, here, and here, because you have this object M sitting here, which represents in some sense the mass of the space-time. The thing that is different is this factor C, which appears here, here, and here. The meaning of the coordinates, U is retarded time, so it's the usual retarded time coordinate up scribe plus. R is a radial coordinate. So it's a coordinate that goes out in that direction. ZA are coordinates on the two spheres that are sections of scribe plus. And what this is essentially is an expansion in powers of R, or more precisely 1 over R. So flat space will be without this. There is a correction of order 1 over R here. Flat space would have an R squared gamma AB. Gamma AB is the unit metric on the unit sphere. So R squared gamma AB is what we usually have, but it's corrected by some things C, here, here, and here, where C is a trace-free tensor, and these indices A and B and this covariant derivative are with respect to the unit 2 sphere. This M, usually you think of M as being a constant, as you would have in the Schwarzschild space-time, but if you have a dynamical space-time, C can be functions of U, then in a dynamical space-time, this M can be a function of U and of ZA. Because this is not the usual mass in the usual sense of the word that you find in Schwarzschild, this sometimes gets a suffix B, and MB is usually called the Bondi mass aspect. You can find a collection of charges, usually called supertranslation charges, that are the integrals over the sphere of any function you like, so this is any spherical harmonic times mb. So there is another collection, infinite collection of charges, and you can describe these in terms of a QF plus, which is defined at the past endpoint of scry plus, and similarly there will be a similar expansion here for what happens on scry minus. You have to replace u by minus v. And then basically it will give you the same thing. So there is an infinite collection of conserved charges between this point, and it works in a very similar way to electromagnetism. There is a flux formula. The flux formula tells you how this charge evolves as you move along scry. So the change in the charge between 2 points is 1 over 4 pi times the integral of between on scry plus between some values of u. So it's du square root of gamma d2z, and you get 3 terms here. TUU is the UU component of the energy momentum tensor, so this represents energy flowing through scry with a minus sign. Limit. And it shouldn't be 8 pi, it should be 4 pi. And then there's a minus NAB, and that comes with a factor of 1/8. And then there is plus 1/4 of dA dB NAB. And we're missing an F. Good, that's the right formula. So, by picking F to be equal to 1, spherical harmonic L equals 0, M equals 0, then what you see is this is basically the same formula for mass loss from an isolated system. There is some matter which is flowing through scry. That's rather like the electric current for the electrodynamical case. Then there is this term here, minus an 8th NAB NAB. NAB is equal to d by du of CAB, and effectively this is the mass loss due to gravitational radiation. So this is matter, gravitational radiation, C, this n, the time derivative of C, is sometimes called the Bondi-News function. And lastly, there is this term here, which, if f is equal to 1, just goes away because you can integrate by parts and it will disappear. But if f is not equal to 1, this has some physical meaning, and this is basically due to soft gravitons. So this is some kind of gravitational charge which is precisely analogous to the electric charges that we had in electrodynamics. The properties of these charges, although it's slightly more complicated as you can see here, are precisely similar to the the electromagnetic charges that we had before. So you can extend these to the horizon as well, and it gives rise to an infinite number of conservation laws. There might be some more gravitational charges, but unfortunately there is no time to describe those. If you want to see them, they are written explicitly in the paper that came out yesterday. So the question is, are these charges sufficient to resolve the information paradox? Let's look at an evaporating black hole again. What we have discovered is an infinite collection of charges which are conserved between here and here. These are gravitational and are associated with any gauge field. So there are some issues here. There are an infinite number of them. So the question is, are these enough or too much to solve the information paradox? It looks like there's an infinite number of them, but you could argue about that. Since the entropy is finite, an infinite number of charges looks like it's too much. So there's a question mark there. We don't know the answer. Point 2. S is equal to a quarter A. The charges that we have found depend on the nature of the gauge fields in question, whereas this does not. S equals a quarter A does not depend on the spectrum of elementary particles. So there's an issue here, sometimes called the species problem, since you would like to say that the charges that you have here, if you don't measure them, would give rise to the entropy. So you can imagine doing that calculation. You just average over all the possible charges that you can have, and you ought to get S equals a quarter A. But if the number of charges depend on the number of species you've got, you are in trouble. The way out of this is there is actually something rather different about the gravitational case, which I didn't really show you. And so we hope that the difficulties there are resolved by the fact the gravitational case is different. I did not describe that partly because we have not yet managed to write up that bit of computations. So I would regard this as a success if you could calculate S without cheating. I would then be convinced that this was right. Of course, it's very easy to cheat. Many have. So that's something that one aims for. But that's not sufficient to resolve the information paradox. You've got to do a bit more. If you look at this picture, it looks like stuff that falls in through there will actually leave the space-time. But nothing peculiar happens when you cross the horizon. It's just simply some other point in space-time that's like any other point in space-time. So you just happily fall off the edge. That will, of course, take all of the information of this matter with it. So if you really believe that, you have got to explain how come you appear to violate the no cloning theorem in quantum mechanics. You have got to explain why this singularity, or apparent singularity, doesn't bother you. And lastly, you have got to figure out how to retrieve the information about the incoming state from the Hawking radiation, the stuff that's coming out here. So those are some challenges. Now let me make one last observation before I stop. The only information that can be preserved using these kinds of methods is information in gauge fields. If any symmetry is a global symmetry, then a global symmetry cannot work. As an example of what I mean by global symmetry, I mean something like baryon number in the standard model. It's not a gauge symmetry, and you couldn't tell the difference between a black hole made of baryons and antibaryons if it really is a global symmetry. There is only one theory which seems to make any sense and contains gravitation and has no global symmetries, and that's string theory. So it seems to me that this is pointing somewhat in that direction, although it is quite possible that our current ideas about what string theory really is aren't really the ultimate ideas of what it actually is. So I think that's a good place to stop. I have to get a taxi and get on a plane.